and systemic effects.
Right.
And usually when people hear metabolism, they think about, I don't know, counting calories or their gym routine.
Or how fast they digest a burger, maybe.
Exactly. But in the microbial world, metabolism isn't about weight loss. Metabolism is warfare.
Exactly. I think most of us grow up thinking of bacteria as these little invading soldiers, right? Like tiny Vikings with helmets and swords storming the castle of our body. And while that's a fun image, the source material we have today suggests that the real danger isn't their swords or shields. It's their chemistry.
That is the core premise we really need to start with. Bacteria aren't dangerous just because they're invaders or because they take up space. They are dangerous because they are master chemists.
Master chemists.
They manipulate redox chemistry, they exploit oxygen gradients, and this is perhaps the most terrifying part, they provoke our own metabolism into self-destruction.
That's the part that got me. The idea that infection severity isn't just about the bug itself.
No, not all.
It's this complex math equation. It's the bug's metabolism,
Oh.
our immune response, and crucially timing. It changes the way you view the symptoms you feel when you're down with the flu.
And that's our mission for this deep dive. We're going to unpack how bacteria breathe, why they force our bodies to heat up with fevers, and why that brain fog you feel when you're sick isn't just in your head.
It's real.
It's a very specific biological mechanism. We want to hand you the blueprint of the battle so you understand exactly what was happening under the hood.
So let's start with something we all think is inherently good. Oxygen. We need it to live.
Right.
We panic without it. If I hold my breath for 2 minutes, I'm in serious trouble. But the notes here call it the oxygen paradox.
It is a paradox. Oxygen is absolutely necessary for complex life, but it is simultaneously toxic.
Toxic. It feels so counterintuitive.
Highly toxic. Think about what oxygen does to the world around us. If you leave a piece of iron out in the rain, what happens?
It rusts.
It rusts. That's oxidation. Oxygen is literally stealing electrons from the metal and breaking down its structure.
Okay.
Now imagine that exact same chemical aggression happening inside a delicate biological cell. When our cells use oxygen to create energy, they don't just produce clean power, they produce exhaust fumes.
And we call these reactive oxygen species, or ROS.
ROS, that's right.
Okay, so let's unpack these ROS. What exactly are we dealing with here? What are these fumes?
Well, the three big ones mentioned in the data are superoxide, hydrogen peroxide, and hydroxyl radicals. And these aren't just, benign waste products. They are molecular wrecking balls.
Wrecking balls.
They're chemically unstable, which means they are desperately looking to steal electrons to stabilize themselves.
And where do they steal those electrons from?
Anywhere they can. They will shred DNA, they'll damage lipid membranes, they destroy proteins. A hydroxyl radical doesn't care if it's hitting a vital genetic sequence or a piece of trash. It just reacts.
So every time I take a breath and my cells use that oxygen to run my body, I'm inadvertently creating tiny amounts of poison.
Essentially, yes, it is the cost of doing business with oxygen. And this is where we have to look at the brain.
Right. The neuroscience anchor in the notes?
Yes. Your neurons, your brain cells, are incredibly sensitive to this oxidative stress.
And why is the brain more sensitive than, say, my skin or my liver? What's special about it?
Two big reasons. First, neurons have huge metabolic demands. They are burning a massive amount of fuel constantly, which means they are creating a lot of that exhaust.
Okay, makes sense.
And second, their membranes are rich in lipids. The brain is effectively a lump of very specialized fat, and lipids are just very, very susceptible to this kind of oxidative damage.
So if oxygen is this dangerous even to us, with all our complex systems, how do bacteria survive it? I mean, they're single-celled organisms. They don't have lungs. They don't have, complex organ systems to filter things out.
They have shields, or more accurately, enzymes. This is the first major battleground in the chemical war. If a bacterium wants to invade a human body, which is full of oxygenated blood, it has to have evolved specific enzymes to neutralize these reactive oxygen species.
It's like a bomb disposal squad.
Precisely. The first shield is an enzyme called superoxide dismutase, or SOD. It takes that first really dangerous superoxide radical and it converts it into hydrogen peroxide.
But hydrogen peroxide is still bad, right?
Totally.
That's the stuff that fizzes when you put it in a cut. It kills things.
It is. It's definitely less dangerous than superoxide, but it's still toxic. If you just leave it there, it will still cause a lot of damage.
So that's why you need the second shield.
That's why you need the second shield, catalase. Catalase takes that hydrogen peroxide and it breaks it down into harmless water and oxygen gas.
So it's a two-step process. SOD handles the initial threat. turns it into a manageable problem. And then catalase comes in and cleans up the leftovers.
Correct. And this gives us a massive clue about what kind of bacteria we're dealing with. In the clinical world, we categorize bacteria based almost entirely on which of these shields they possess.
Right, the clinical logic in the notes. Let's break that
You
down
can
because
do
this
it.
seems to determine
Let's
where
work
an
today
infection
to make
can actually
tomorrow
happen in
a
the body.
better day.
So first you have the obligate aerobes. These are bacteria that
do
need
it.
oxygen
Let's
to
work
survive,
today to
just
make
like us.
tomorrow a better
Because they live in
day.
an oxygen-rich environment, they
You
possess
can do
both
it.
shields,
Let's
SOD,
work.
and catalase. They are fully protected against the rusting effect of oxygen.
Okay, that makes sense. If you live in the fire, you need a fire suit. Then you have the adaptable ones?
The facultative anaerobes. These are the versatile survivors. They prefer oxygen because it gives them more energy, but they can live without it.
So they also have both shields.
They also have both because they can exist in oxygen.
But then there's the third group, the ones that sound, well, like a nightmare.
It's the obligate anaerobes. These bacteria have neither SOD nor catalase. They have no shields at all.
Which means what?
Which means oxygen literally kills them. If you expose them to fresh air or oxygenated blood, the reactive oxygen species build up instantly and just tear them apart. They simply cannot survive in an oxygenated environment.
That is fascinating. It explains why certain infections happen in very specific places.
Yes.
If I have a deep puncture wound or really damaged tissue where the blood supply and therefore the oxygen supply is cut off, that is a playground for these anaerobes.
Exactly. They're hiding from the fresh air. They thrive in the necrotic dead tissue where the oxygen concentration drops to 0.
And for the bacteria that do have shields, specifically catalase doctors have a very specific list they memorize. The notes call these the catalase-positive organisms.
Yes, this is a critical list for medical students and clinicians. A must-know.
I do love a good mnemonic. The notes list places for your cats. Can you walk us through that?
It's a classic medical school memory aid. CATS refers to catalase. And places stands for the specific bacteria. Pseudomonas,
Okay.
Listeria, Aspergillus, Candida, E. coli, Staphylococcus, and Serratia.
Wow. That is a rogues gallery of nasty bugs. Pseudomonas, Staph, E. coli. I mean, these are the heavy hitters of hospital infections.
And knowing this list matters because these organisms are just much better at surviving our body's own immune defenses. Our immune cells, specifically neutrophils, actually try to use what we call oxidative bursts. They literally throw oxygen bombs at bacteria to kill them.
That's incredible. Our immune system weaponizes the very toxicity we were just talking about.
It does. But if the bacteria has catalase, it can disarm those bombs. It takes the hydrogen peroxide the immune cell throws at it and just turns it into water.
It's like shooting at Superman. The bullets just bounce right off.
Pretty much.
Okay, so some bacteria use enzymes to survive oxygen. But the notes mention another enzyme that's used for something completely different. For hiding.
Yes. Coagulus. This is less about chemistry survival and more about tactical positioning on the battlefield.
The concept here is biological bunkering. That sounds intense. What is coagulase doing?
So coagulase is an enzyme that converts fibrinogen into fibrin. Now, fibrinogen is just floating around in your blood, totally inert, waiting to be used.
Right.
When it gets activated into fibrin, it becomes a mesh. It's what causes blood to clot.
So normally we use that to stop bleeding when we get a cut.
Exactly.
Yeah.
But these bacteria, and Staph aureus is the classic example, they use it to build a wall. They secrete coagulase, which causes a clot to form specifically around them.
So they're building a fortress.
They are. By cladding themselves in this fibrin clot, they create a physical barrier. Immune cells can't get to them. Antibiotics have a really hard time penetrating that wall.
And the notes mention this leads to walled-off purulent infections. That sounds like the literal definition of an abscess.
That is exactly what an abscess is. It's a localized infection where the bacteria have bunkered down. You have a center filled with pus and bacteria, surrounded by a thick wall of fibrin that the bacteria built for themselves.
There is a really interesting neuroparallel here in the notes. They compare this to isolating circuits behind barriers.
Yes, it's a great comparison. Think about how the brain handles damage. If you have a stroke or a trauma, the brain forms a glial scar. It isolates the dead tissue to protect the healthy neurons around it.
It's a strategic isolation.
It is. The bacteria are doing the exact same thing, creating a do-not-enter zone to control their environment and protect themselves.
It makes treating those infections so much more difficult because you can't just throw pills at it. The medicine floats around in the blood, but if the bacteria have built a wall that blocks blood flow, the medicine never arrives.
Precisely. That is why the treatment for an abscess is often incision and drainage. You have to physically break the bunker to let the medicine in.
So we've looked at their defenses, shields against oxygen, and bunkers against the immune system. Now, if we move from defense to offense, or maybe more to the engine room, we find one of the most critical differences between us and them, the electron transport chain, or ETC.
This is the energy war, and this is probably the most philosophical part of the biology we're discussing today.
I remember the ETC from high school biology. It's how cells make ATP, the energy currency of life. It's the powerhouse.
Right. Both bacteria and our own mitochondria use an electron transport chain. They work on the same basic principle, passing electrons down a line to charge a battery. But there is a massive life or death difference in how they operate.
Let's start with the bacteria. What does their engine look like?
The bacterial ETC is located in their plasma membrane, their outer skin, essentially. And its superpower is one word: flexibility.
Flexibility.
The bacterial engine is like a hybrid car that can run on gas, diesel, electricity, or even cooking oil.
Meaning they don't just need oxygen to run the engine.
Exactly. They prefer oxygen. Oxygen is high-octane fuel. It gives the most energy. But if the oxygen runs out, they don't stall. They just switch inputs.
They can just use something else.
They can use nitrate or sulfate as electron acceptors. They can shut down parts of the chain or reroute power. They are incredibly, incredibly adaptable.
Okay, now compare that to our engine, the mitochondria inside our cells.
Our mitochondria are located deep inside our cell. Their ETC is on the inner mitochondrial membrane, and they are like a high-performance Formula One engine.
Okay.
They are incredibly efficient at producing massive amounts of ATP. They are tuned for speed and power. But
There's always a but.
they only run on high-octane fuel. They must have oxygen.
Zero flexibility.
Zero. If the oxygen cuts out, the mitochondrial engine doesn't just slow down, it suffers catastrophic failure. The electrons pile up, the gradient collapses, and energy production stops instantly.
And the source material drops a really cool evolutionary insight here. It says mitochondria are essentially streamlined bacteria.
It's the endosymbiotic theory. It's widely accepted now that billions of years ago, our ancestors were single-celled organisms that swallowed a bacterium.
And instead of digesting it,
They formed a partnership. That bacterium became the mitochondria.
we have little bacteria living inside us, powering us.
We do. But over billions of years, that mitochondrion gave up all its flexibility. It stripped away the genes for using nitrate or sulfate. It focused entirely on becoming the most efficient oxygen-burning machine possible.
It traded survival skills for raw efficiency.
Exactly.
But there's a cost to that efficiency, and that cost is fragility.
A huge cost. This is the life or death consequence mentioned in the outline. Because our neurons depend entirely on that high-efficiency mitochondrial engine to maintain their electrical signals, they cannot handle a lack of oxygen. Hypoxia low oxygen kills neurons within minutes.
Whereas the bacteria
just switch fuels. They switch to nitrate or sulfate and keep on chugging. This explains why, in a severe infection where oxygen delivery is compromised, like in sepsis or pneumonia, your brain cells start dying long before the bacteria do.
We are driving a Ferrari that stalls if the wind changes, and they are driving a tank that runs on mud.
That is a very, very apt analogy. And this difference in engines leads us directly into how the infection plays out over time. It's not just about who has the better engine, it's about the timeline of the invasion. We need to talk about the growth curve.
Right, the timing of the attack. The notes break this down into 4 phases: lag, log, stationary, and death.
It sounds simple, almost like a business cycle, but the trap regarding treatment lies in the details of these phases.
Walk us through it. The bacteria enter the body. What happens first?
First, you have the lag phase. This is the setup. The bacteria have just entered the body, but they aren't dividing yet. On a graph, it looks like nothing is happening.
Are they dormant?
No, not at all. They are extremely active metabolically. They are sensing the environment, checking the temperature, the pH, the oxygen levels. They're turning on specific genes and synthesizing the enzymes they need for that specific host.
So they're tuning their metabolism to me, specific.
To you, they are loading their weapons.
It's the calm before the storm.
Precisely. Then comes the log phase. This is exponential growth. 1 becomes 2, 2 becomes 4, 4 becomes 8. They are dividing rapidly.
And this is where the trouble really starts.
This is where it starts. And here's the crucial point. This is when toxin production is often at its highest. They are building cell walls, secreting proteins, and taking over.
And this is usually when we feel the sickest,
Yeah.
right? When the numbers are exploding.
Yes. And logically, you'd think, okay, lots of bacteria, let's hit them with antibiotics right now. And technically, bacteria are most susceptible to antibiotics during this phase.
Why is that?
Because many drugs work by attacking the machinery that builds new cell walls. If they're not building, the drugs don't work as well.
But the outline mentions a key insight here, a trap. Killing bacteria during the log phase can actually worsen inflammation. Why? If I kill them, shouldn't I get better?
You will, eventually. But immediately, it can get ugly. Think about what happens when a bacterium dies. It doesn't just vanish, it bursts.
Like a balloon.
Like a balloon filled with poison. If you have millions of bacteria actively producing toxins and building structures, and you suddenly blow them all up with antibiotics, they release everything at once.
Oh, wow. It's like carpet bombing a chemical weapons factory.
That's a great analogy.
You destroy the factory, but you release all the gas into the air.
Exactly. You get a massive surge of inflammatory components, toxins, cell wall fragments flooding the system all at once. This triggers a massive immune reaction. We call it the Jerisch-Herxheimer reaction in some cases.
What does that look like for the patient?
Their fever spikes, their blood pressure might drop, and they feel significantly worse, even though the treatment is working.
That is terrifying.
Yeah.
You're doing the right thing, treating the infection, but the immediate result is a spike in danger.
It requires a steady hand from the clinician. Then, of course, comes the stationary phase, where nutrients run out, and then finally the death phase. But that log phase trap is something you always have to be aware of. The cure can feel like the disease for a few hours.
Now, speaking of feeling terrible, let's talk about fever. I always thought fever was just something that happens, like the engine overheating because it's working hard. But the notes say it's a weaponization of heat.
It is absolutely a weapon. It is not an accident. Your body isn't just running hot. Your hypothalamus, the part of your brain that acts as a thermostat, intentionally resets the set point.
It chooses to do this.
It chooses to do it. It decides to burn more energy to cook the invader.
So my body is willing to make me miserable to kill the bug.
Yeah.
How does the heat actually hurt them?
It works on a molecular level. Proteins and enzymes have very specific, intricate, three-dimensional shapes, and those shapes depend on temperature. If you heat them up too much, they unravel. We call this denaturing.
Like cooking an egg white. It turns white and solid.
Exactly. And once you cook that egg white, it can't go back to being liquid. The heat denatures bacterial enzymes so they stop working. It also disrupts the fluidity of their cell membrane, making it leaky. And primarily, it slows down their replication. Basically, it makes the entire environment hostile for the bacteria.
But it's hostile for me, too. I feel awful when I have a fever. My joints ache. I'm completely exhausted.
That is the cost of the weapon.
Yeah.
To generate that heat, your body has to ramp up its metabolism. You have to shiver to create mechanical heat. You consume more oxygen. You burn through glucose reserves. It's incredibly expensive.
And looking at the neurocaution in the notes, it says high fever increases excitotoxic risk in brain tissue. What does that mean?
Right. Remember, the brain is already sensitive. Now you are heating it up. Heat increases the metabolic rate of neurons, meaning they need even more oxygen and sugar just to stay stable.
But if you are sick, you might not be getting enough oxygen or eating enough sugar.
Exactly. The supply is down, but the fever is forcing the demand way, way up.
And what happens then?
If the fever gets too high, neurons can become overexcited. That's the excitotoxic part, and actually burn themselves out. They damage themselves. It's a very risky strategy. The body is betting that it can cook the bacteria before it cooks its own brain.
It's high-stakes poker with your own biology.
Indeed. And while the body is using heat, the bacteria are using chemical warfare. We need to talk about toxins. The notes break these down into exotoxins and endotoxins.
The snipers and the grenades.
I like that distinction. It fits perfectly. Let's start with the snipers. Exotoxins.
These are secreted proteins, right? The bacteria are making them and shooting them out?
Yes. They manufacture these specific proteins and shoot them out into the surrounding tissue. They are highly specific and unbelievably potent.
So give me some examples of these snipers in action.
Well, think about neurotoxins. These specifically target nerve cells. Tetanus toxin, for example, travels to the spinal cord and blocks the signal that tells muscles to relax.
So you freeze up?
You lock up, rigid paralysis. On the flip side, you have botulism toxin. It blocks the signal for muscles to contract. You go limp.
Wow.
These are snipers because they don't destroy the whole house. They just cut the specific phone lines to disable the entire system.
And then there are enterotoxins.
Those target the gut lining, causing massive fluid secretion diarrhea. It's a way for the bacteria to spread themselves. And then you have cytotoxins, which are a bit cruder. They just pop cells open to eat the nutrients inside.
So those are the precision weapons. What about the grenades? The endotoxins?
Endotoxins are fundamentally different. They aren't secreted. They are actually part of the bacterial body itself.
Part of its structure.
Yes. Specifically, a component called lipid A, which is found in the outer membrane of all gram-negative bacteria.
So the bacteria is wearing the bomb vest.
In a way, yes. As long as the bacteria is alive and intact, the endotoxin is mostly contained. It's just part of its wall. But when the bacteria
You can
dies,
do it.
or when our
Let's
immune
work
system
today
rips it
to make
apart,
tomorrow a
that
better
lipid
day.
A is
Okay.
released.
And this connects right back
You
to what
can
we said
do
about
it.
the log phase
Let's
and
work
antibiotics.
today
It
to
does.
make
When
tomorrow
you kill
a
the
better
bug,
day.
you release the lipid A.
Okay.
Exactly. And
You
unlike
can
the
do
snipers,
it.
lipid
Let's
A
work.
doesn't target a specific neuron or a specific muscle. It targets the immune system itself. It triggers a massive systemic alarm.
The notes call this the immune explosion.
When lipid A hits the blood, immune cells release a storm of cytokines. These are chemical messengers that scream emergency to every single organ in the body.
And what is the result of that scream?
It leads to fever, massive vasodilation, which means your blood vessels widen and your blood pressure drops, and eventually septic shock.
So the endotoxin isn't killing you directly like a poison. It's not stopping your heart or your lungs on its own.
No.
It's tricking your immune system into blowing up the building to catch the burglar.
That is a perfect way to put it. It causes a dysregulated host response. And that leads us to the most dangerous systemic effect of all, sepsis.
The notes define sepsis as a dysregulated host response to infection. I feel like that's a polite way of saying total metabolic chaos.
It is chaos, but it's chaos with a pattern. The immune system causes the organ failure, not just the bacteria. And the mechanism is metabolic collapse. We need to trace this because it explains the symptoms we see in the hospital.
Let's trace it. So it starts with the blood pressure dropping, right? The vasodilation.
Yes. The cytokine storm causes vasodilation. Your blood vessels get bigger. That means your blood pressure plummets. When pressure drops, you aren't pushing enough blood and therefore enough oxygen into your tissues. We call this hypoxia or ischemia.
And we know what happens when our cells don't get oxygen. The Ferrari engine, the mitochondria stalls.
It stalls instantly. But your cells don't want to die. So the body is forced to shift from aerobic metabolism, using oxygen, to anaerobic metabolism without oxygen.
It tries to run on the backup generator.
It does. But human anaerobic metabolism it's dirty. It produces a nasty byproduct, lactate, or lactic acid.
I know lactic acid from working out. It's that burn you feel in your muscles when you sprint too hard.
Right. Now imagine that burn happening in every organ in your body simultaneously. Your liver, your kidneys, your heart, your brain.
Oh, man.
As that lactate accumulates, the pH of your blood drops. You go into metabolic acidosis. Your entire body becomes acidic.
And why does that matter for the brain? This is the brain fog connection, right?
This is the critical link. pH is fundamental to everything, but especially enzyme activity and neurotransmission. The notes mention that low pH specifically affects NMDA and AMPA receptors in the brain.
What do those receptors do?
They are the primary receptors for learning, memory, and cognition. They are the switches that allow neurons to talk to each other. They are absolutely critical for higher thought.
So when the blood gets acidic, those switches stop working.
They literally malfunction. Their chemical structure changes and they get blocked. So the brain, at a physical level, stops communicating effectively.
This is a huge aha moment for me. When you have the flu and you feel confused or you can't focus or you feel like you're in a dream state, it's not just that you're tired. It's that your blood pH and your cytokines are physically suppressing your synapses.
Exactly. It's not psychological, it's mechanical. And the cytokines themselves also play a direct role. They don't just signal inflammation, they cross into the brain and alter synaptic transmission. They reduce long-term potentiation, which is the biological basis of forming new memories.
So the brain fog is functional, the hardware is glitching.
It is. And the source material notes that delirium is often the first sign of sepsis, especially in older patients. Before the fever, before the blood pressure drop, the brain starts to misfire because of these metabolic changes.
The brain is the canary in the coal mine.
It's the first thing to show signs of trouble.
That is profound. It really drives home the idea that you can't separate the infection from the host's reaction.
You really can't. And if we look at Section 8 of our outline, the causal chains, we can see how all these dots connect. It's helpful to visualize the domino effect.
Let's walk through one of those chains, the anaerobe chain.
Okay. Imagine a deep wound. Domino, 1. You have an anaerobic environment, no oxygen.
Okay.
Domino 2. Obligate anaerobes thrive there, and the host tissue shifts to fermentation to make energy. Domino 3. That produces lactate.
Right, the acid.
Domino 4. The lactate builds up, causing acidosis. Domino 5. The acidosis disrupts the NMDA receptors in the brain. The result: confusion and organ dysfunction.
It's a direct line from a wound in your leg to confusion in your brain, connected entirely by chemistry. What about the endotoxin chain?
Domino 1. Gram-negative bacteria die. Domino 2. They release Lipidae, the endotoxin. Domino 3. That hits the immune cells, which release a storm of cytokines. Domino 4. Cytokines tell the hypothalamus to raise the temperature, that's your fever, and the blood vessels to dilate, that's shock. Domino 5. Blood pressure drops.
And the hypoxia chain. That follows right after.
Right. Domino 1. Low oxygen delivery due to shock. Domino 2. The mitochondrial ETCR Ferrari engine fails.
No energy.
Domino 3. No ATP is produced. Domino 4. Neurons, which have incredibly high energy demands, stop functioning. The result is neuronal dysfunction and rapid cell death.
It's relentless. The math of it is it's inevitable. Once the dominoes start falling, it seems so hard to stop them.
It is. And this brings us to the memory lock, the core philosophy of this whole deep dive. If you remember one single thing, it should be this contrast.
Bacteria survive by flexibility.
Yeah.
Neurons die from inflexibility.
That is the summary of the entire war. Bacteria are metabolic survivals. They can switch engines, build bunkers, and change their chemistry to suit the environment. Our most advanced cells, our neurons, are locked into a high-performance, high-dependency mode. They are brilliant, but they are fragile. Sepsis is simply what happens when that metabolic control is lost.
It really changes the way I see antibiotics and treatment, too. It's not just kill the bug, it's kill the bug without crashing the system.
Precisely. You have to manage the chemistry of the host just as much as you manage the population of the invader. You have to keep the Ferrari running while you try to blow up the tank.
So as we wrap up this deep dive,
Yeah.
what's the final takeaway? We've gone from oxygen toxicity to bunkering enzymes to the complete collapse of the brain.
I think the takeaway is that infection is a chemical negotiation. It's a transfer of electrons. It's an enzyme blocking a receptor.
Yeah.
It's a very, very microscopic battle with macroscopic life and death consequences.
Right.
We tend to focus on the symptoms, the fever, the pain, the fog, but those are just the smoke. The fire is happening in the electron transport chains and the protein structures.
It makes you appreciate how complex the balance of health actually is. We are walking a tightrope of redox chemistry every single day.
Well, we are, and usually we stay on the rope. But when a bacterium with the right set of enzymes pushes us, we can fall off very, very quickly.
Here is a provocative thought to leave you with, listeners. We always talk about how humans are the pinnacle of evolution. We have these massive brains, complex societies, consciousness, but physically, chemically. We sacrificed our resilience for that power. We gave up the ability to run on sulfur or nitrate so we could think about philosophy.
It is the ultimate trade-off. We gained the world, but we became metabolically fragile. Meanwhile, the bacteria, they kept it simple. They didn't upgrade the engine, they just made sure it could run on anything.
So in the end, who is really the survivor? The one who can write a symphony but dies without oxygen in 4 minutes? Or the one that can live in a clot, eat sulfur, and wait for the dinosaur or the human to die?
If survival is the only metric, the bacteria are winning. They were here long before us, and they will likely be here long after us.
Something to think about the next time you get a fever. You aren't just sick. You're in a high-stakes chemical war. Thanks for diving deep with us.
Stay curious and stay oxygenated.
See you next time.